As we know, one of the major channels in order to study gravitational wave sources is by assuming we have a massive binary on a wide orbit and invoking mass transfer events that can alter the orbital architecture of the system. In my case, in order to understand and constrain the uncertainties in this evolutionary channel, I use a combination of MESA and population synthesis models, in this case, Star Trek. So one of the major uncertainties in this channel is that regardless of whether we're using MESA or population synthesis, we kind of are not sure of how stars expand in the first place, in particular massive stars. Here you can see two examples of different prescriptions and models. On the left-hand side, you can see the MESA models from Poseidon. And on the right-hand side, you can see the Star Trek / population synthesis models, plus the addition of the blue area there representing the HR region beyond the Humphrey-Davidson limit. So the first thing to notice here is that we have more and more differences the higher we go with mass. The second interesting thing to say here is that when we reach very high masses, like 100 solar masses or 150 solar masses, stars, according to MESA, just kind of like go directly leftwards towards the walkaway stage, while instead the population synthesis models completely overestimate the expansion of stars and go directly to the red supergiant branch. So here you can see a rough estimate of stellar expansion according to different models. So here you can see on the y-axis here, the maximum expansion that single stars can reach throughout the whole lifetime as a function of their initial mass at 10% solar metallicity for different MESA models and for rapid analytical models used in population synthesis, with an additional observational constraint coming from a rough drawing of the Humphrey-Davidson limit. So first thing to see here is that different prescriptions for MESA bring to strikingly different radial expansion. And MESA additionally prescribe in these models that stars expand well beyond the Humphrey-Davidson limit. The second thing to notice is that regardless of these inherent uncertainties of MESA models, rapid analytical models for population synthesis still manage to overestimate stellar expansion up to 1 order of magnitude. So the first question here to ask is, does overestimating stellar expansion lead to an overestimation of mass transfer rates? The answer here is that it depends. If we look at this plot over here you can see the number of common envelope events in my synthetic population over 32 different metallicities that lead a binary to evolve into a gravitational wave sources as a function of the radius of the donor star at the onset of the common envelope and its initial mass. The 4 orange lines here represent the same MESA maximum radius models that I showed you in the previous plot. So if we kind of looked at the ZAMS masses below 40 solar masses, we could say that regardless of which expansion model we adopted, most of stars would initiate common envelope events well before they reach their maximum radius. So overestimating stellar expansion doesn't necessarily lead to overestimating the initiation rates of mass transfer events. If we instead go above 40 solar masses, this is instead a problem because our models are more uncertain. And depending on which radial expansion models, we get pretty different results. And on top of that, most of the common envelope events within this mass range are initiated well beyond the Humphrey-Davidson limit. So all these common envelope events might not exist in the first place. But even below 40 solar masses, we have an additional problem because as you can see here from that plot, roughly most of the common envelope donors are within 600 solar radii of expansion, let's say. But in order to survive the common envelope event, we need stars that have a deep convective envelope, which means that they kind of have to be red supergiants and roughly, let's say, debatably above 600 solar radii. So what we need to survive common envelope events are white binaries, which are exactly what we statistically lack. So here in this plot over here, you can see another approach to what I just said before. So here in this AJ diagram, you can see my population of stars at 10% solar metallicity that either lead to the formation of the gravitational wave source in red, or that lead to an early stellar merger within a common envelope event in gray. So canonically, we have quite a good amount of binaries that can survive common envelope events. But if we instead took into account the need of a deep convective envelope, we have a different picture. So here you can see the vertical green line over there that is a rough estimate from MESA simulations of where the stars form a deep convective envelope. And you can see that if we took it as a survival condition, everything on the left-hand side of this green line should lead to a merger, an early merger, while only the few binaries that are on the right-hand side will transform in gravitational wave sources. So if this is just the population that we have at hand, we cannot justify our gravitational wave observations. So we either need to invoke another evolutionary channel, or maybe we must find other solutions like stability criteria. But here we just talked about population synthesis. The problem is that we have also big uncertainties in stellar evolution models and MESA in general. So the development of a deep convective envelope and also the stellar expansion are deeply bound to a series of factors, among which we have stellar winds. So canonically in MESA, we know that there is what we know being an outdated prescription for wind mass loss rates, which is what is known as the Dutch wind prescription. That just gives us mass loss models for red supergiants, optically thin winds, and optically thick winds, meant as Wolf-Rayet winds, which Wolf-Rayet winds need a dedicated wind mass loss prescription because they have lost a lot of envelope mass, but their luminosity levels are almost unaltered. So their luminosity over mass ratio is quite high. So they have enhanced mass loss rates. But this is just a poor approximation of where we have thick winds mass loss. So the point is that also very massive stars, so say above 100 solar masses, have very high luminosity to mass rates. So they also have Wolf-Rayet-like winds. And it's not just a theoretical mambo jumbo. We see these objects. They are called WNHs, and they are also main sequence stars with hydrogen-rich envelopes that behave like Wolf-Rayet stars. So I brought in my MESA study a new wind mass loss prescription that is a combination of homogeneous and clumped thin winds and different thin winds mass loss rates, also with different initiation requirements. And I developed a grid of models at solar metallicity. So two things are important to see here. The first one is that I would like to focus you the most on the orange and the blue colors, which are the Wolf-Rayet winds. So if we consider them as Wolf-Rayet winds, and if we go very above masses, we can see that at the highest masses, stars already start their evolution that they are behaving like Wolf-Rayet stars. They are not expanding at all. They are going directly towards the Wolf-Rayet branch. So it means that they cannot expand and initiate mass transfer events. The other important thing here that maybe it's more important for observers than us, okay, 2 minutes, thank you, is that if we assume that 20 solar masses at SAMS is the minimum mass at solar metallicity in order to produce black holes, we can see here that all the black holes progenitors at solar metallicity have a previous phase when they are Wolf-Rayet stars. And with these new mass loss rates, we also get new black hole masses. So this plot represents the black hole masses as a function of the initial mass for my models in blue and from other two studies in green and orange. And you can see that it's very hard to produce very heavy black holes. The heaviest black holes in my population, in my Mesa population, is at 300 solar masses at ZAMS at 28 roughly solar masses. So if in solar metallicity environments, we see black holes that are heavier than these, it doesn't come from stellar evolution alone, at least. And with this, I guess I'm done. I'm done.
Questions?
So you had a figure with the maximal radial expansion of stars as a function of mass, where you draw the Humphrey-Davidson limit. How did you turn the luminosity effective temperature in mass radius?
Well, I mean, I just look at the age arc diagram at the very at the lowest luminosity that the stars will enter the Humphrey-Davidson limit, and from there I just interpolated the stellar charts from Star Trek, and for each of these masses I just registered the first point in expansion that they went beyond.
And related to these, like, because that the Humphrey-Davidson limit is just an empirical limit where we don't see many stars. Right?
Yeah.
So does this plot, like, do you interpret this plot as, well, those MESA models have to be wrong because they spend a lot of time in that region of the HR diagram?
I would say not. I would say that what this plot says is just that if the Humphrey-Davidson limit actually exists for some physical reason, that reason, at least for 10% solar metallicity, doesn't come from stellar evolution, and maybe comes from binary interaction.
Or that it isn't currently accounted for in our stellar evolution models.
Yeah. But for instance, if I may add a small thing that I forgot, for instance, in my new wind mass loss models, the Humphrey-Davidson limit is respected.
I have a question as well. It's really interesting to see what you have these, or was there someone else? Sorry.
You can ask. Yeah, go for it.
So basically you're saying that you have these 300 solar mass stars, right? That lose 270 solar masses in winds.
Yeah.
Obviously they're never going to be binary black holes.
No.
What are they going to be? What are the observations that we should be looking for? There's just super dust and shrouded black holes hanging out there.
I don't know if dust is the right way of calling the environment. I'm not sure.
Solar masses of wind.
Yeah.
Yeah, but there's a very hot UV sources in the middle, so it's gonna.
Oh, it will be black hole.
Oh, we want to. Yeah.
It died.
By the time you form the black hole, that material is gone.
Is it gonna be gone?
I mean, it's gonna be leaving at 3,000 kilometers per second, right, or 5,000 kilometers per second.
Okay.
I mean, if it's just that if you don't have a gravitational pole, maybe you don't have the dust orbiting around the system anymore.
I guess my question was just, do you think there's any observables that we should be looking for to test if, losing 200 solar masses versus losing 50 solar masses is a big difference?
Well, I mean, if the observable for saying that, I mean, if I can say it another way, you are asking if there is any empirical proof that our mass loss rates are right?
Yeah.
I mean, but that's exactly the best-selling paper, because that's exactly how he found those mass loss rates. So he looked around the stars and he saw that they were ejecting that amount of material. And he said, yeah, that's it.
Yeah. Oh, great, thanks.
Hello?
Yeah.
This is maybe a little bit of a vague question, but some people have suggested that the Humphrey-Davidson limit is more of a soft limit, and that maybe the stars do go there, but first they're very massive and they live a very short time, and maybe they only spend, let's say, 1% or 5% of their evolution time in that region. Do you have any thoughts on that?
Well, yeah, I mean, technically, I believe that probably the reason why we observe or don't observe the Humphrey-Davidson limit must come from several different reasons depending on the context. Maybe if I didn't check any other metallicities that weren't solar metallicity, so probably something like that might also expand a bit more before actually you go into the Wolf-Rayet phase. So maybe at lower metallicities, you have that expansion.
So do you think it would, I wonder if you could sort of do this again, but let's say a 10th solar and see if you can get the same limit too?
I mean, I was chatting with Tomer before about checking Wolf-Rayet stars observed in the SMC. So yeah, it's coming. It's coming.
Very cool.
Yeah, more questions? We have enough time for about one more question.
It's very technical, but it's gonna bore us.
That's you?
The other ingredient that comes into the radii of the stars, especially at those luminosities, is the treatment of this super Eddington completely inefficient layer. What are you using here?
Eddington factor. I put an with like conversation with Bestelener. We kind of like try to understand where to put the threshold for thick winds. And we elected that a good approximation will be setting an Eddington factor above 0.5, roughly, for the initiation of.
That's a surface Eddington factor.
Surface Eddington factor.
Because, but how are you treating the layers that might become super Eddington just inside?
Well, I mean, that's the prescription that is MESA that takes the luminosity and abundances from the surface, not just the very last cell.